All right, so I guess let's go ahead and get started. So when it comes to essentially our physics base we're looking at now, we're looking at Newtonian physics with a twist. So objects are going to stay in motion or stay with a lack of motion unless they're acted upon by an external force. Okay. Its acceleration of a rotating body is directly proportional to the torque that's causing it. And it's going to be the same torque that's felt on both sides. So it's equal and opposite. So for a reaction, there's an equal and opposite reaction. We're just literally talking about getting something to spin. Now, when torque is applied from one body to another, the second will go ahead and produce that same torque on it. So when you're trying to rotate something, you also have to receive those same rotational forces. So first concept we have is going to be what's known as essentially what's resisting that accelerating on the rotation speed. And that is our moment of inertia. Now, this is the thing that any object has. One moment. Specifically, when we're talking about rotating bodies. So this is what's going to resist angular acceleration. So it's going to be both the speeding up and the slowing down. It's going to be based upon the mass of the object and its essential distance that it's distributed over the axis. So essentially something that happens to be wider and heavier is going to have a greater amount of moment of inertia. Now, the way we're going to figure out this moment of inertia is we are going to take the sum, that's what the sigma stands for, of the mass of the object around its radius. So we could have here is a baseball bat that effectively has a very, very heavy weight at the knob end. And so even though there's a lot of mass and a larger radius on this side, in turn, this mass is so much longer that it's going to compensate for it. Okay. Now, the next concept when it comes to essentially rotation is what's known as the radius of gyration. So this is where we're going to find essentially the greatest amount of the mass and effectively the radius essentially congregating, so to speak, where it kind of balances out. Now, this is important because when we think about the radius of gyration, I want you to think about the body when it's moving. So if our hip is going to be the thing that we're rotating upon, when we happen to have our leg in a straight position, the center of mass of the calf and the center of mass of the foot is the furthest from our hip. So it actually requires a greater amount of inertia that we have to overcome. Meanwhile, when we happen to be in that bent knee toe up position while we're sprinting, in turn, we're going to be able to shorten these lever arms and we're going to, in effect, be able to essentially lift that leg with less resistance. So the easy way that you can experiment with that right now is literally lift your leg up as high as you can with your knee bent and then lift your leg up with that leg straight. We then have angular momentum, just like we have linear momentum. And this is going to be a combination of that inertia multiplied by this is a lowercase omega. And this is the essentially symbol for angular velocity. Okay. So H, angular momentum, equals R, inertia, multiplied by R, angular velocity, or we can look at it as the mass of the object multiplied by the radius squared, multiplied in turn by the inertia. Okay. Now, why we care about angular momentum is it tends to be conserved. So what this means is we tend to keep the same momentum going irregardless of the amount of external torques that we have acting upon it. Now, what this effectively means is when we're looking at someone do something like a backflip, doing a spin in figure skating, what we're really looking at is they have the same amount of angular momentum. The key is they're changing one major variable so they can spin faster. Okay. What's the major variable that they're changing? Okay. That in turn is going to change another aspect. So the momentum stays the same. Go ahead, Jake.
Is it where the center point is as they spin?
Now the center point is going to stay the same. What instead is changing when it comes to concepts of inertia? We're changing
the length.
Bingo. So the radius changes. So that's why when people are trying to spin, they tend to pull themselves into a much tighter position. So this is why people are tucking themselves. Okay, I have no idea what this is about. So effectively, what we're looking at is the mass of the individual is staying the same when you're doing, backflip, standing or otherwise. The key thing is they're getting into a much smaller tucked position. And so effectively, since their inertia, specifically due to the radius decreasing, because notice it's radius squared, their rotational velocity is naturally going to increase to a much greater degree. So how we're going to get a change in angular momentum is going to be based upon what's known as the angular impulse, which is just like impulse, which remembers force times time. Well, now instead we've got torque times time equals the change in inertia. So we have effectively our final angular inertia, and we subtract our initial angular inertia. And that's going to go ahead and give us the information on effectively how much of a change we had in the first place. Now, this is going to happen when we do things like we do that takeoff for things like a backflip or otherwise, is while we're on the ground, we're going to be pushing off of it aggressively, setting our body backwards, lifting our arms in order to create this initial angular momentum. Now, once this is going to be related to the amount of torque we've applied and the time we had to do it, and from there, now that we're in the air, all we can do is essentially maintain the same angular momentum, just changing that body position. So this chart, and this is going to seem familiar to you guys because obviously it happens to be in your equation slide. So really all we've got here is how we're converting from linear to angular. So when we have linear, we just worry about mass. When we have angular, we worry about inertia. When we have linear, we have force. With angular, we have the force times the distance, which gives us torque that we really care about. Momentum, we can see the key difference between angular momentum and normal momentum is simply going to be that radius squared. And then finally, impulse is typically force times time. Angular impulse is going to be that force times the distance from the axis multiplied by time. So torque times time gives us angular impulse. So when we go back to our Newtonian physics concepts, when it comes to the angular law of inertia, any object is going to maintain that state of rest or constant motion unless it is acted upon by an external force. Angular acceleration is it's always going to be the torque is what's causing our angular acceleration, okay? And that's going to be in proportion to the torque that's being produced to the object, the direction the torque is being produced, as well as inversely proportional to the body's moment of inertia. So if the object is a heck of a lot bigger and heavier, turns out it's not going to accelerate as much. It's going to turn in the direction of the torque. And if the torque is huge, it's going to increase and accelerate at a massive rate. So mathematically, what we have there is our torque equals our inertia times our acceleration. Okay. Our torque equals our inertia times our acceleration. Now, there's also the angular law of reaction. So for every angular action, equal and opposite reaction. So what you exert on it, it exerts upon you. Okay. And this is important when we're getting to things like centripetal and centrifugal force. Centripetal force is as an object is spinning about an axis. Think about like certain amusement park rides where effectively you're in an object that's spinning at a very high speed and it's pulling you up against the wall. If you guys have ever had a chance to do those, does that sound familiar to some of you guys?
I know what you're talking about, but I've never been on one.
Okay, that's fine. So the wall is what is essentially producing that centripetal force because it's pushing into the center. You, on the other hand, are feeling what's known as centrifugal force, and that's you being pulled into the wall behind you. Now, the same thing's going to happen when you're throwing a discus. you're throwing a shot put. When you're throwing a discus and you're spinning at that high rate of speed, your fingers are producing that centripetal force to keep that discus from falling out of your hands. Whereas the disc itself is producing that centrifugal force upon yourself. So equal opposite forces. So that is really the keys of the data or the information that I wanted to go through with you guys. So what questions do you guys have? What do you guys want to work through? Callie, what question do you have? No questions, Callie?
Sorry, I was trying to find the unmute button. I came in a little bit late. Could you go over like the first two slides again?
No worries. So we're talking about going through the basics of the physics there?
Yes, sir.
No worries, no worries. So it's going to be the same basic physics concepts that we talked about with linear Newtonian physics. The key thing is now we're just literally spinning it. That's it. So objects are going to stay in motion unless they're acted upon, or stay at rest unless they're acted upon by an external force. So it's okay, we need to apply a torque in order to get something to rotate or to slow down. If we're not talking about drag, which we're not bringing up for the most part in this class. Now, acceleration is always going to be related to the torque that happens to be causing it. And it's going to be the same direction of the torque, and it's going to be inversely proportional to the amount of inertia. So, for example, if I'm going to go ahead and take my hand and just try and spin this pen, I'm creating a torque on it to turn it. Pen's pretty darn light. It's not really that hard to use that force. Now, if I try to do the same thing using just two fingers and try to spin my cat, I'm probably going to not accomplish spinning the cat, and the cat's just going to probably take a swipe at me. So the torque is going to be the same direction. So notice I turned it going what would have been counterclockwise, and it would move counterclockwise. And notice inversely proportional to that inertia. Then when a torque is applied by one body to another, the second body will exert an equal and opposite torque on the first. So, for example, just think about when you're trying to throw a spiral on a football. As you're creating that force on the football to turn it, the football is resisting that turn. So every force that you produce is in turn having to be absorbed by not just the object you're acting upon, but yourself as well. So does that make sense, Callie?
Yes, it does. Thank you.
Cool. Moment of inertia is simply going to be when we take the sum of all of the masses multiplied by the radius squared from the center of the object. And so we're going to sum this up all together. If we look at this example of a heavy weight at the end of a baseball bat on the knob. And so we've got that radius squared multiplied by the mass, plus that radius squared times that mass, and that, all of them summed together, and that gives us our inertia. So that kind of catch up on what you missed?
It did. Thank you so much.
Anytime, Callie. Gracie, what questions do you have?
I'm pretty good. I think I got it all.
Okay. So when it comes to your guys' homework, specifically when you're going through and trying to do that superhero homework, what are we really looking at? What are you guys trying to now utilize that we have here to figure out answers to those questions? Okay, that's all right. So when you're thinking them through, ask yourself, are we talking about linear or rotational physics? And if we're looking at rotational physics, okay, so now obviously we're going to have to try to figure out inertia at some point. So we've got the mass and the radius. We can be looking at angular momentum, and obviously how's that going to change in different situations? Okay, and that would be thanks to effectively how does torque play into it? And so if we're changing the angular momentum, how much torque and then how much time to do that over? So with every one of the examples that you guys are going to look, you're going to be able to essentially look up the weight of the object. You're in turn probably going to be able to figure out what would be not just the mass of the object, but you're probably going to get a good idea of the radius, or you're going to make your best estimate. Then from watching the scenes, you're going to be able to see the time component of how long that torque was applied for, etc. And from there, you're going to be able to solve for the answers throughout. So, well, guys, if you don't have any other questions and you're feeling good, that's the rest of the slides. No one's got any other questions? Nothing else you guys want to go through, talk about?
Yeah, so I was trying to pull the homework up.
Mhm.
For the speed of the car on the Black Panther
Mhm.
scene, is there an equation for that, or do we just kind of do a rough?
So when you're looking for the velocity, well, obviously you can, I don't think they actually show the speedometer on the scene. So instead, what you're trying to look at is get a concept for effectively what would the velocity be given other landmarks you can see, or once again, ballpark of something realistic. So you're saying the car was
Okay.
going 300 miles an hour, like, okay, that's a little wrong. And you say it was going 5 miles an hour, okay, that's wrong as well. But trying instead to kind of look at, okay, given the velocity that it seems like it would have to have been going, given those conditions, okay, now moving forward, da 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 da.
Gotcha.
Well, shoot, guys, if you don't have any other questions, that's it. That's the rest of the rotational physics. You guys have all the tools you need. Also, another component to make sure we're doing whenever we go way, way back earlier, when we're looking at specifically our summation of torques, is keep in mind your muscles don't pull in a straight line. You still have to do some trigonometry, meaning if we go ahead and are looking at the elbow holding a weight at 90 degrees, what the heck? Oh, that's interesting. The biceps actually going to pull in an angle. And so that angle, in turn, we have to figure out the actual vertical force vector, because part of its pulling vector is actually going to be keeping the elbow in the socket. It's actually pulling it back into the socket. So be ready to not just figure out your normal effort times effort arm equals resistance times resistance arm, and the sums of obviously all of them on one side to the other. But once we solve for that effort, we still need to typically do a little bit of trig and figure out what that actual force would be, since the angle is not perfect. Does that make sense to you guys?
Yeah.
Awesome. Well, guys, have a great day. Make sure we're staying on top of our homework for the class, working on our labs. And really, you guys have all the tools now to start breaking down the actual torque, force, acceleration, everything you need for your group's projects. So, try to start working on those. If you're having issues, obviously feel free to go ahead and ask any questions you want inside of class. I will see you guys on Tuesday. I don't really want to keep going just because you guys want to lecture ahead and we can do some more stuff and keep getting our learn on, and hopefully everyone isn't drowning whenever we see them again. letting you guys vote on it. You guys want to keep going?
I think we should be good where we're at. Should be a little nice to everybody.
Are you sure about that? You sure you don't want to just keep on going? Keep on keeping on?
I'm positive.
Okay, that's what I like. I like a degree of certainty there because, otherwise we're going to have a lot of fun talking about the joys of the spine. Whoa. Oh, cool. I guess I'm back there. All right. Anyways, you guys stay safe out there. Come with any questions you guys have. Work on those assignments, and we will see you guys soon. All right, guys. Bye-bye.